Okay, we're going to do quiz number 23. And so let's see, as I look at this problem, we have sinusoidal input or AC input, and we're trying to find the final voltage. Okay, so if we can convert this circuit to phasor domain, this would convert to an impedance. We'd have two impedances in parallel that we could combine, and then this voltage is across that combination of impedances, so we could use a voltage divider equation to get the final voltage and then convert back to time domain. All right, so if we try to pursue, to implement that our evil plan, we convert this into the phasor domain. So this voltage is going to be 64 phase of 0. Okay, that's 64 magnitude, and the phase here is 0. And now we're going to have an impedance associated with this capacitance. The resistance, of course, is still 2 kiloohms. And then the inductor will have an impedance there. All right, so we kind of have to figure out what these impedances are. Remember, the impedance for a capacitor, we're going to have, Z of the capacitor is minus J over omega C. And for an inductor, Z of an inductor is going to be J omega L. All right, so in our case, omega is 8,000, and the capacitance C is equal to 31.25 nanofarads, and L is equal to 500 millifarads. Okay, so if we go back to try to compute these, and let's see, I have this little IPython notebook pulled up where I defined, I have a little function that converts to polar, rectangular, and in parallel. So let's see. We have 500 milli. Is that what L was? L is 500 milli, and then 31.25 nano. So C is going to be 32 point, or 30, let's see, was it 31.25, and then e to the minus 9. Let's see, let me just make sure. 31.25 nano, 500 milli, and then omega is 8,000. So we'll put 8,000 in here, and then omega, or ZL, is going to be J omega L. ZC is 1 over J omega C. Let's see, and we have a resistance here of 2 kiloohms. All right, so I'm going to put in here 2,000. All right, and then if I print, let's see, so I'm going to get rid of some of this, and I'm going to go ahead and print out ZL, and I also want to print ZC. All right, so if I run this guy, and then I'm going to get, colon, okay, rerun. Okay, so I get ZL is going to be 4,000 J, and ZC is minus 4,000 J. So I can come back here. This is going to be J 4,000 and minus J 4,000. So my capacitor, my capacitor is minus, inductor is plus. So my capacitor is minus J 4,000. My inductor is J 4,000. Okay, so now I can come and I can convert this into, we've got the 64, we've got 64 phase of 0, and then I'm going to have a, inductance or a impedance here of minus J 4000, and then I'm going to combine these two impedances in parallel. And this parallel impedance here is going to be what, 2000 times J 4000 divided by 2000 plus J 4000. So let's see. Let's come back here, and I'm going to do, I'm going to say, okay, I want to do, let's see, I'll just call it ZP is equal to, and then I have my little function there, parallel, and I'm going to put, I need R in parallel with ZL. And then I need to print ZL. Okay, and I'm going to go ahead and, whoops, just need to go back up here and run that cell. Okay, when I do that, I get 4000J, as you can see here. All right, so the parallel combination of the two, I don't really believe that. Let's just kind of go back and look at this. So I have RZL, let's see, oh, sorry, I needed to print ZP. And I'm going to go ahead and run that cell again. Okay, and it's going to be 1600 plus 800, or 1600 plus 800J. So this guy here is, this is equal to 1600 plus J 800. So I've got my 1600 plus J 800, and that is the, well, in phasor domain it's V0. Okay, so this guy here is going to be V0 related back to that guy. All right, so voltage divider says that V0 is going to be the 64 phase of 0 degrees. And then I'm going to do my voltage divider. I'm going to have my 1600 plus J 800 divided by 1600 plus J 800 minus J 4000. Okay, and let's see. I'm going to come back here. So I need to have, let's see, down here, I'm going to do, so I want to find, yeah, I'm going to do ZP, and then I want to divide by, so in other words, yeah, well, maybe I should go ahead and do my voltage source here. So VS is going to be, so I have this little function, and the rectangular function here just simply takes magnitude and phase and turns it into a rectangular complex number. So I'm going to do rectangular, and I have 64 and 0 degrees. Okay, so if I run that, I need to print. Sorry, it's hard to type on this guy. Okay, so I get 64 plus 0J, and then my V0, 0 is going to equal Vs times, and then I'm going to have Zp divided by Zp plus, and then I have my capacitance, right? Zc. So if I come back here, yeah, it's going to be, here's my Zc. So I've got to have Zp and Zc. All right, so that should be V0. And so I want to now print V0. So if I run that, I get, let's see, this doesn't quite look right. What did I do wrong? So Vs times Zp divided by Zp plus Zc okay, and then and then I need to convert this into polar. So again, I've got this, I've got a little function up here that takes a rectangular complex number and turns it into polar. So if I just do, if I come down here and convert to polar, so let's see, actually I'm just going to print out the polar part. And V0. So if I print it out in polar, it's 32 with a phase of 90 degrees. Think about that for a minute, because it was 0 minus J. I think it should be minus, well, okay. Yeah, 32, 90 degrees. All right, so the answer back here was 32 phase of 90 degrees. All right, so when I convert that into time domain then, V0 of t is going to be 32 cosine of, I'm going to use this same omega t, 8,000 t plus, and then I've got the, 90 degrees. And the units here are going to be the same units back here. This is the units of the 64. So it's in terms of volts. And there is the answer.